In this module, we're going to focus on the first three sections of Chapter 7 of your textbook. We're going to be looking first at linear algebra, some properties of matrices and vectors, and then we'll get into determinants and linear systems. A few features of matrices. Most of these will be familiar to you. Some will need more review than others, and some will already be experts at this, I recognize, and you'll want to just speed through these and get right on to doing this week's quiz. The size of a matrix might be described as m by n, where m is the number of rows and n, the second of those, is the number of columns. A square matrix has the condition where the number of rows is equal to the number of columns. If you're looking at the diagonal of a square matrix, then you're looking at the terms A11, A22, all the way to ANN of a n by n square matrix. And so that will often be focused on the diagonal of a square matrix when we get to more advanced applications. Two matrices are said to be equal if and only if they happen to be the same size and the corresponding elements of each of the matrices are also equal. And that's those conditions have to be met for equality. Vectors can be represented either as a row or a column vector. A vector A, and notice you'll see that I have it in bold but not in a capital letter to represent a vector. That can be represented either as a row vector, where it is a one row by n column row vector, or a column vector where it is m rows and one column. So you can represent the same terms, the same vector, as either a row vector or a column vector. And if we're only thinking about a one-dimensional feature, then it doesn't matter whether it's a row or column vector. But once we introduce matrices, then we have to specify whether we're describing a row vector or a column vector. Mathematical operations on matrices are probably familiar to you. Scalar multiplication would be simply a scalar multiplied by the matrix, and to do that for an m by n matrix A and a scalar C, you would just take the scalar C and multiply each of the terms of the matrix by that scalar, and now you would have a you'd scale up or scale down each of the terms according to that value of C. Matrix addition is applicable for two matrices of the same size. So in order for addition or subtraction to be defined, you'd need to have the two matrices be of exactly the same size. In matrix multiplication, we have to recognize that sometimes the product of two matrices is simply not defined. And also when multiplying matrices, order matters. So let's take a look at how the product of two matrices is defined. The product C, defined as the multiplication of matrix A times matrix B in that order of an m by n matrix A multiplied by an r by p matrix B, is defined if and only if r is equal to n, and then the result C is of order m by p, with the entries as defined by follow. As shown in this equation. You've probably seen this at some point in the past, but as a reminder on how we define order and whether or not the two matrices can be multiplied, take a look at this visual where you'll see that if A is an m by n and B is an r times p matrix, those don't have to be square, and all that you need to have is you need to look at the inner two terms, n and r. And if those two numbers are the same, then you'll be able to multiply the two matrices. What will be the size of the product? To find that, you just cross out the common number and you're left with m by p, and in fact that's the size of the product that results, m by p. So that's how we define multiplication for matrices as shown. So again, order does matter. Matrix multiplication is not commutative. It It is very important that you notice that A times B is not necessarily equal to B times A. In fact, it will very rarely be true that A times B is equal to B times A. It can happen, but it often is not true. You can have A and B defined and B times A not defined. Um, and as again, it could easily be true that one result above may not be defined or may be of different size than the other. Vectors in multiplication. A row vector and a column vector can be multiplied. A column vector and a row vector can be multiplied. But these two results are not the same. And when we take a look at some examples of matrix and vector multiplication, those two statements will be better understood. So take a look at these different examples. Here we have 4 different examples. In the first case, we have a 3 by 3 multiplied by a 3 by 1, and the end result is a 3 by 1. In the next example, in the next row down, you'll see that we have a 1 by 3 multiplied by a 3 by 3, and the end result is a 1 by 3. Notice that in these first two examples that the column vector 5, 1, minus 1 is not the same as the row vector 3, 3, minus 1. So you get completely different results when you multiply a 3 by 3 by a column vector and a row vector by that same 3 by 3. So we get very different results, and they're even of different magnitude, but even though these first two examples show that you get a vector result, those two vectors aren't the same. Next, we consider the example of a 2 by 1 multiplied by a 1 by 2, and the end result is a 2 by 2 that's shown there. And the last result on the bottom there, you'll see that we have the case of 1 row and 2 columns multiplied by a 1 column 2 row, so a 1 by 2 multiplied by a 2 by 1 gives you a 1 by 1, or which is actually just a scalar. So notice that in these last two examples we've shown that if you take a column vector and multiply it by a row vector, you have a square matrix of that's full. And in the last example, you see that if you have a row vector multiplied by a column vector, you end up with a scalar. So you get very different results. So order matters in multiplications for both vectors and matrices. Next, we're going to consider the linear transformation in a matrix form. And if we're looking at the case of two equations with two unknowns, we might be familiar with those equations written as y1 is equal to a11 times x1 plus a12 times x2. So we have variables y, x1 and x2, and constants a11 and a12, and the end result, our next equation is y2 is equal to the constant a21 times the unknown x1 plus the constant a22 times the unknown variable x2. All those can be written using vectors and matrices, where we define the variable vector y as a column vector that consists of the components y1 and y2. Then we have a matrix of these constants, and you'll see in this case it's a square matrix. A11, A12, A21, A22 are just the constants that define this linear transformation. And we also will have the x variable, x1 and x2, and we can write this system of equations as the column vector y is equal to the matrix A times the column vector x. So we need to take a system of equations with two equations and two unknowns and recognize that it can be written in matrix and column form as shown, that y is equal to A times x. One of the other properties of a matrix, which we'll sometimes need, is to define the transpose of a matrix. The transpose of an m by n matrix A is an n by m matrix that we write in the form A transpose. The first row of A becomes the first column of A transpose. The second row of A becomes the second column of A transpose, etc. Notice that some of the properties of transformation are that if you take A and take its transpose, get that result and takes the transpose of that, you get back to A. Moving to the right, you'll see that if you take A plus B, that sum, and transpose it, you'll get the same thing as if you took the transpose of A plus the transpose of B. Similarly, you can take the scalar C multiplied by the matrix A and take the transpose of that result, and you'll get the same thing as if you first take the transpose of A and then multiply it by the scalar C. If you're looking at matrix multiplication, it's tricky. If you are looking at the product of matrix A times B that you then take the transpose, that would be equivalent to the transpose of B multiplied by the transpose of A. Notice that we actually had to switch the order of multiplication when we took the transpose of the product. So that's just a particular peculiarity to keep in mind when we're discussing or describing the transpose of a matrix. We have a number of different special matrices that come up from time to time. Some of these are very useful. One case would be a symmetric matrix. In the case of a symmetric matrix, you'd have the transpose of A being equal to A. So a symmetric matrix is equal to its transpose. A skew symmetric matrix would be defined by A transpose is equal to the minus A, and that sometimes occurs in some applications. In this course, one of the properties that we'll sometimes need is an upper triangular matrix. In this upper triangular matrix, that's a square matrix with 0 entries below the diagonal, and the only non-zero entries are on the diagonal and above the diagonal. Similarly, a lower triangular matrix is a square matrix that has 0 entries above the diagonal, and the only non-zero entries are on the diagonal and below. We might also have a diagonal matrix, which you could imagine is defined by having non-zero terms only along the diagonal, and all of the terms would then be 0. We could have a scalar matrix, which is simply a matrix of size 1 by 1, and you're used to those. Those are just real numbers. And also we could have a unit matrix. A unit matrix is a particular thing. It's a square matrix. It's also a diagonal matrix. But what's unusual about a unit matrix is that all the diagonal terms are 1. So it's a diagonal matrix where all the terms along the diagonal are 1, and all the other elements of the matrix are 0. So that would make up a unit matrix. I think we're ready for section 7.3 at this point. And in 7.3, we're being introduced to linear algebra, where we consider matrices and vectors and systems of linear equations. So you probably already are very familiar with systems of linear equations, and in this case we would have m equations with n unknowns, and you probably already know it would be great if m and n are the same, but they don't in general have to be. But what's shown here constitutes a linear system of m equations with n unknowns, and in matrix form it's written as ax equals b, or I could have said ax equals y, but we more typically write ax equals b. And in this case, the coefficient matrix is what A represents. So A is a set of coefficients, B is a scalar, B is a column vector that represents the values from this set of equations from b1 down to bm in a column vector, and x becomes our unknowns. X is a column vector that contain the various unknowns of x1, x2, all the way to xn. So both x and b are column vectors. The augmented matrix is it's a shorthand way of describing a system of linear equations. The system of linear equations shown in the previous slide can also be described fully with an augmented matrix, where you just take the coefficient matrix and then add on, and we usually do add this vertical line, but not always. In shorthand I don't always include it, but we usually include that vertical line and then the column vector b tagged on to the end, and then that would be called the augmented matrix. Here it's shown as A tilde, and the augmented matrix contains all the same data needed to solve the representative system of linear equations, and is a common way of writing this in shorthand in engineering analysis. So it's something I'd like you to get used to, the augmented matrix. Let's take a look at a particular example of a three-variable example, and in this case we have three equations, and we'll have the three unknowns x, y, and z. And if we wanted to write these as in the matrix form, we would end up with, notice the constants 3, -1, and -1 show up as the first row in our 3 by 3 matrix. The next equation gives us 1, 1, -1, and that shows up as the second row of our matrix here. We have our unknowns x, y, and z represented as a column vector, and then we take our numbers -2, 2, and 0 and use those to form a column vector shown here on the right. And that's how we represent a system of three equations with three unknowns in matrix form. If we continue with the same example, then our three equations are obtained from creating or completing this matrix multiplication, and we represent the equations in our shorthand augmented matrix form with that vertical line, and then we just have a single matrix. That's the augmented matrix shown there at the bottom. And those two different versions of representing this system of equations actually represent the same thing. So you do need to get used to that shorthand. To solve systems of linear equations, we're going to perform elementary row operations on our augmented matrix. Elementary row operations are defined as three possible things. So there's three things we can do and have a valid elementary row operation. We can interchange two rows. The second thing is we could have the addition of a constant multiple of one row to another row. And the third thing that we can do is multiplication of a row by a non-zero constant. So those are the only things that we're allowed to do in elementary row operations. We put those together in order to solve systems of linear equations, and we do that using a process that we call Gaussian elimination with back substitutions. In this method, we apply elementary row operations to the augmented matrix to transform the coefficient matrix A to an upper triangular form. Once we perform those operations, we'll have the upper triangular form and we're ready to apply back substitution. And in this process, we work from the bottom up to generate the solution vector. Once you have the results of step one, you have your upper triangular form. Your last row will consist of one equation with one unknown and one variable, and you'll be able to have one element of your solution vector identified. Once you have that solution identified, you use that in the row above, and you work your way up from the bottom to the top, and you're able to find your solution. Many of you have done this before, some of you haven't, and I think it's best understood through examples. So I urge you to take a look at those examples until this becomes familiar to you. When we're looking at systems of linear equations, we have a number of special cases. The first of these will be a homogeneous system. A homogeneous system has a b vector that is all zero values. A non-homogeneous system will have at least one non-zero component in the vector b. A system of equations will have one of several different possibilities. It can have no solution, which is called an overdetermined system. It can have one unique solution, which is called a determined system. And it can have an infinite number of solutions, which is called an underdetermined system of equations. A consistent system has at least one solution, and an inconsistent system has no solution. The rank of a matrix is sometimes going to be a property that we discuss, and we note that when we apply Gaussian elimination, and it's been used to reduce the augmented matrix as much as possible to prepare it for back substitution, then it's in what we call row echelon form. The number of non-zero rows in that portion of the augmented matrix the number of non-zero rows in that portion of the augmented matrix that constitutes the coefficient matrix, so everything but the last column, is known as the rank of the matrix. So if you end up with all zeros on the bottom of your coefficient matrix, then you have a rank less than the number of rows that you had in that coefficient matrix. So you'll see this in application, but basically that's the way to determine the rank of a matrix, is to reduce it down to its row echelon form and then count up the number of non-zero rows. Vectors and vector spaces are something that we are all familiar with. Whenever you've plotted something in 2 dimensions, you've seen things in a 2-dimensional vector space. If you could plot things in a 3-dimensional system, you would have a 3-dimensional vector space. And in general, we say that vectors can be combined in linear combinations of the form C1 times A1. Again, notice that the C1 is a scalar and A1 is a vector, so we can have a linear combination of m vectors that we've just made a linear combination out of. If we write the equation so that they together sum up to represent the zero vector, and notice that that zero in that second equation is bold, so it represents the zero vector with all zero terms. If the only combination of scalar C1 through Cm that allows this equation to be satisfied are all zero, then vectors A1 through Am are said to be linearly independent. You're familiar with linearly independent vectors. When you plot things in 2 dimensions, you have the x vector and the y vector, and those are certainly independent. But an example of 2 vectors in that space that would not be independent would be, suppose you have a vector pointed in the positive x direction and a vector pointed in the negative x direction. Those would not be linearly independent. Vector spaces, linear independence, and vector bases. Imagine a 2-dimensional vector space and imagine a 3-dimensional vector space. In each vector space V, we can define any vector as a combination of the other vectors that constitute a basis. We commonly do this using vectors along the axes of a coordinate system, but other vectors could be used as well. And a linearly independent set of vectors in the vector space V that constitute the maximum number of vectors that are independent in space V is called a basis for V. Consider this two-dimensional example of a vector space, one you're very familiar with. We have an x and a y axis, and they're perpendicular or orthogonal, and we're used to considering this in this two-dimensional vector space. But we could add another vector, vector A, and still another vector, vector B, shown here, and we could actually make unusual combinations, because in reality, and I'm not looking at anything three-dimensional here, but x and a are linearly independent, and x and a together would form a basis of this two-dimensional vector space. That's the screen or the page that you're looking at this on. A and y would form a basis of this two-dimensional vector space. X and y, x and b, b and y. But a and b would not form a basis of this vector space because they don't fully populate the vector space. You couldn't get to every other combination through a and b. But with x and a, you could have a linear combination of x and a that would form y. You could, it would be a and x would be an awkward basis for this vector space, but they are a valid basis for this vector space. But a and b are the only vector combination here that would not form a valid basis for this vector space. That's enough for this module, and I'll talk to you again next week.